In this video, we're going to look at increasing and decreasing functions and relative extrema. So generally, we would say if a function is increasing, that it is going up. Or in other words, if it is rising, specifically that means as x gets larger and larger, the y values or the function values also get larger and larger as we go from left to right. So from left to right. It's decreasing if f is going down as we move along from left to right. In other words, as x increases. So, for example, here's a real simple function on the right. On what intervals is this increasing and decreasing? So let's put an arrow here and assume it keeps going in those directions, which it does because it's a cubic. So it's increasing where it's going up as we go from left to right. So on out from negative infinity, it's going up, 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 all the way to x equals -1. So it's increasing from negative infinity to -1. And then it's decreasing from -1 to 1. Those are the x values. And then it begins increasing again after x equals 1. So from 1 to infinity. If x is increasing at a particular value of x, let's say x equals a, if you look at everywhere where the function is increasing, those are the two pink sections of this function here, the slopes of the tangent lines are positive. In other words, the derivative at every point where the function is increasing is greater than 0. And everywhere where the function is decreasing, at every little point in there, the slope of the tangent line is negative. So f prime of a is less than 0. A function has a relative maximum at a point if it's a maximum near that area. So really you can say if you can draw a circle around it, and within that circle this y value is the highest, then that's considered a relative maximum. So this function only has one relative maximum right there. So we'll say a function f has a relative maximum at x equals c if f of c is greater than f of x for x near c. And a function f has a relative minimum at x equals c if f of c is less than f of x for x near c. So right here, this is a relative minimum. We can draw a circle around it, and within that circle, that's the lowest point right there. Also, this one is as well. Relative extrema don't occur at endpoints if we have a closed interval, because if you were to draw a circle around it, there's nothing going on over here on that side. So we don't consider relative extrema to occur at endpoints, although absolute extrema may occur at endpoints. Okay, now let's look at the types of places where the function changes from increasing to decreasing, or from decreasing to increasing. So as we go along, it's decreasing, decreasing, and then boom, right there, it changes and it starts increasing. In this particular case, it looks like the derivative is 0. The slope of the tangent line is horizontal. Okay, then it's increasing up to here, at which point it changes to decreasing. Again, the derivative is 0 there. And right here, the derivative is undefined because we have a sharp point. So if f changes from increasing to decreasing, or vice versa, those changes occur at places where either the derivative is 0 or undefined. In other words, critical values. Therefore, the relative maximums and minimums of a function occur at critical values. So if you're looking for relative extrema, that's where you look. You look at critical values. And let's break it down with the first derivative test for relative extrema. So for any continuous function f that has exactly one critical value c inside of an open interval ab, let's sketch that up here. So here's an open interval a to b, and somewhere inside of that we have a critical value we're going to call c. So if c is in between a and b, notice they're not in alphabetical order from left to right, okay? And we know c is a critical value, then we can determine whether or not f has a maximum or a minimum based on how its derivative changes from the left side of C to the right side of C. So if f prime of x is less than 0 on AC, so that means if f is decreasing, right, the first derivative is negative where the function is decreasing, on the interval from A to C, that's from here to here. And then f prime of x is greater than 0, so f is increasing on the interval from C to B. So the function goes from decreasing to increasing. Then we must have a minimum, right? It says then f is blank on AC, that's decreasing. And f is increasing on the interval CB. And so f has a minimum because it changes from decreasing to increasing. So it must have a minimum at x equals C. Okay, second case, if f prime is greater than 0 on A to C, then f is increasing on that interval. And if f prime is less than 0 on C to B, then f is decreasing on that interval. So if a function changes from increasing to decreasing, follow my mouse, it must be going up and then down, and therefore it must have a relative maximum at x equals C. And you might add the words relative in there if you want. Relative minimum and relative maximum. And if f prime has the same sign on both the intervals from A to C and from C to B, then f is either increasing from here to here and it continues increasing from there to there, or it's decreasing from here to here and it continues decreasing from there to there. And so f has neither a max nor a min, or we'll say f has no relative extremum at x equals C. Let's look at an example. So f of x equals negative x cubed minus 3x squared plus 9x plus 12. Let's find the critical values. Then we're going to make a table to determine the intervals on which f is increasing and decreasing. And then we're going to use the first derivative test to find where the relative maximums and minimums of f occur. And then we'll actually find those relative max and min values. So let's begin with the critical values. So we need to find the first derivative. So we'll have negative 3x squared minus 6x to the first plus 9. And we need to solve for where is that undefined? Well, it exists everywhere because it's a simple quadratic. So we also need to find where it equals 0. To simplify, I'm going to take a negative 3 out of everything, leaving me with x squared plus 2x minus 3. And then if we divide both sides by negative 3, that just goes away. And let's see if this will factor, hopefully. Does, let's see, how about x, positive 3 minus 1, yep, that should do the trick. So x equals 1 and negative 3 are the critical values. So let's label CV for critical values. Now let's make a table to determine the intervals on which the function is increasing and decreasing. We're assuming that we don't have a picture of the graph in front of us, and we're going to use information about the derivative to do this. So what I recommend doing is putting your critical values on a number line. We're going to use this as a way to break down a chart. So we want to spread the critical values evenly out, even if it's not to scale, because I'm just making enough room to write, okay? So what this means is that, oops, I did that backwards, negative 3 and at 1. What this means is that these are critical values. So therefore, those are places where we may have relative extrema, and that's the ultimate goal in this problem, is to find the relative maximums and minimums. So we're going to look at the critical values to see if we can figure that out. Sorry about that. Okay, so to do that, we're going to look at the first derivative on each interval. We know that the function only could possibly change from increasing to decreasing or vice versa at critical values. So it's either increasing or it's decreasing on the entire interval from negative infinity to negative 3. And it's either increasing or decreasing on the entire interval from negative 3 to 1. And it's either increasing or decreasing on the entire interval from 1 to infinity. So what we need to really do is just plug in one little test value within each of those three intervals into the derivative to see if f prime is positive or negative. So let's pick a test value. Let's see, how about We'll keep it simple. X equals -4, X equals 0, and X equals 2. And we're going to plug those into the derivative because we want to find where's the derivative positive and negative, because that will tell us where f is increasing and decreasing. So we need to figure out f prime of -4, whether it's positive or negative. And taking a look at this here, I'm going to go ahead and write in the -3 there, because that's another version of f prime. I am going to look at this version of f prime. It's easier to plug into the factored version generally here because you don't need a calculator to do it. So f prime of -4 would equal -3 times -4 plus 3 times -4 minus 1. All we need to figure out is whether this is positive or negative. So it's -3 times -4 plus 3 is -1. And -4 minus 1 is -5. So we have a negative times a negative, which is a positive, times another negative, so f prime of 4 is less than 0, which tells us that f is decreasing at -4, and therefore it must be decreasing on that whole interval, since it could only change from increasing to decreasing or vice versa at critical values. And then we do the same for each of these intervals. So we need to find f prime of our test value 0. It would be -3 times 0 plus 3. So it's a negative times a positive times 0 minus 1 is negative. A negative times a negative is positive. So f is increasing on that interval. And then plugging in 2, f prime of 2 is negative times 2 plus 3 is positive times 2 minus 1 is positive. So it's going to be negative. So f is decreasing on that entire interval. So let's write that out. So it's decreasing on -infinity to -3, increasing on the interval from -3 to 1, and decreasing on the interval from 1 to infinity. That's our answer to that part. And if you like to sketch in some little dashed lines to kind of separate what's going on here, that's fine. Okay, now we're going to use the first derivative test to find where the relative maximums and minimums of f occur. Okay, so what the first derivative test says is that if f prime changes from negative to positive, then because f is changing from decreasing to increasing, we must have a minimum right here at that critical value. And here f prime changes from positive to negative, therefore f changes from increasing to decreasing. Therefore, we have a max at this critical value. Okay, and we need to find the actual maximum and minimum. So we need to find f of -3, and we need to find f of 1. F of x, let's go copy it down here, is -x cubed minus 3x squared plus 9x plus 12. So -x cubed minus 3x squared plus 9x plus 12. Let's double check that. Yes, okay. So we just plug this into the original function here, plugging in -3. -3 all cubed is going to be -27 minus 3 times -3 squared is positive 9 plus 9 times x is -3 plus 12. So we get 27 minus 27, those two terms cancel. Then -27 plus 12 would be -15. And we said that was a minimum. It's a relative minimum, actually. And then f of 1, let's see, negative of 1 cubed is -1. 1 squared is 1, so -3 times 1. Then plus 9 times 1 plus 12. See, this comes to -4. Plus 9 is -5. Plus 12 is 7. And that must be our max.